I will now introduce our next speaker. I'm going to leave the podium because sorry. I just, our next speaker is Kat Cosgrove. The charity is Electronic Frontier Foundation, which will be featured in the Discord later. And Kat has a hidden talent. Kat is a cyborg. So I would take that to heart. And the title of Kat's talk today is Snakes on a Car. We are bursting with curiosity. Please give a warm chat welcome to Kat Cosgrove.
Hello, everyone. I assume if you can't hear me, one of the organizers will tell me that you guys can't hear me. So I think we're good. But hello, thanks for having me. And welcome to Snakes on a Car, or Over-Engineering a Toy. So first, a little bit about myself. My name is Kat Cosgrove, and I'm a developer advocate at JFrog. Before that, I was actually an engineer here on the IoT team, and once upon a time, we built a really flashy, complicated demo proving that updating the software on a car doesn't have to be as time-consuming and inconvenient as it currently is. Now, some cars can be updated over the air. Teslas are a good example of that, though it can take a couple of hours and the car isn't usable during installation. Most cars require you to physically take the car to a service center for the update. I have a whole technical deep dive talk on how we built that proof of concept, and I give it a lot, but there isn't room in that talk for my favorite thing about the work that I did for that proof of concept, building a miniature self-driving car. It was super fun, and you can build one too. Before I get into the talk, if you want to get a hold of me later, I'm on Twitter at Dixie3Flatline, and all of my slides and links to relevant resources will be up at that bit.ly link sometime this afternoon, plus a raffle for a Switch Lite and a copy of Animal Crossing for anybody watching on Twitch who does not have a Switch. We couldn't get an actual full-size normal Nintendo Switch. I don't think anybody can, but we've got Switch Lites. So what is this demo? For JFrog's user conference last summer, we built this proof of concept demonstrating fast, reliable over-the-air updates for edge devices. We went with a car as our example because it's really flashy, and it's not something that a lot of us think of as an IoT or edge device, even though it totally is. You hear IoT device and you think of something really small. You think of your smart light bulbs or whatever. But the reality is that there are 3 or 4 computers in your car. The brakes are probably fly-by-wire. It's not being handled manually. A computer is doing that. Your transmission has a computer. Your infotainment system is a computer. A car is a data center on wheels now. And since JFrog, very reasonably, wouldn't buy us a real car to potentially brick, we had to build our own, inspired by a hackathon I'd run a few months earlier for a local coding boot camp. I will spare you the details since this isn't the talk for it, but we took updates on the car from something that could take hours and required physically flashing the device like Jaguar did when they had to issue a widespread recall for the F-Pace to fix a problem with the braking system, terrifying, to around 35 seconds for an application update, and 5 to 10 minutes for a full firmware update, both without interrupting the driver at all. The application update could happen silently, not that I think it should, but it could. And the firmware update happened mostly in the background, even while the car was being driven, and actually took place when the car restarted. So it didn't really interrupt the driver. We had a pretty robust pipeline in place. So everything was automated from the moment a developer pushed code. It relied on Helm, K3s, Mender for the over-the-air updates portion, Yocto for our custom Linux distributions, and Artifactory for storing Yocto's build cache to speed things up a little bit more. It might sound kind of easy from this description that we just like glued a whole bunch of open source projects together, but it's actually a shockingly difficult problem to solve for, especially if you're trying to take into account things like differing hardware or network unreliability. So from a technical perspective, it was pretty cool. But it also looked really cool. So we had a racing simulator set up in the middle of a huge track, complete with pedals, a race wheel, a screen for the driver, and a green screen around the perimeter of the track. And that's me making sure everything was set up before the conference opened the first day. I was super, super nervous. I'm like clenching my jaw in that picture. We allowed people to interact with it in one of two ways: as a developer, writing and pushing updates for the car, or driving the car while someone else updated it. And I know doing live coding demos is always risky, but we were outrageously confident in what we built. So we really did let like actual randos off the conference floor write code and push it to the car. So it only barfed like once the first day. There was some rockiness, but we rolled back and fixed it. So here is what you need to build your very own miniature car, teach it to drive itself, and make some cool modifications so that it's easier to use it to harass your partners, roommates, or pets. So let's start with the basics. Our car began its life as something called a donkey car, and they're pretty fun on their own. They're also pretty accessible for a lot of people. It's not super difficult to build one. If you aren't familiar with donkey cars, I super was not when I heard about them at a Python meetup. It's a miniature RC car that's been modified with a Raspberry Pi and a camera. The library that enables it to do its thing is called Donkey, hence donkey cars. And in its most basic form, you can build one for like $250 in parts and a couple of hours of your time. Once everything is set up, you just record 10 or so laps. Takes at least 10 to be able to reliably not just veer off into the distance on a track marked with like brightly colored masking tape, or if you have a really dark floor, you can even just lay down some like printer paper. You just need high contrast. Then you dump the recorded images and steering data back to your computer and train a model. Donkey does include a CLI that makes all of this as easy as possible, but the project itself is pretty well documented. So if you want to dig in a little bit deeper and start getting weird with it, you totally can. We did. They're really fun, and a whole community exists around these things just for modifying them with bigger batteries or more powerful motors and nicer wheels to race them against each other. The standard camera is just a regular Raspberry Pi cam. They're really, really cheap, but some folks do add a second camera for stereo vision or a LiDAR camera for better depth perception. Ours was only a little bit beefier than the standard donkey car since we were forcing it to do more work than it was built for, but not by much. We swapped out the Raspberry Pi 3B for a 3B Plus with a compute module, and that's what's pictured here. So I'm kind of extra, and we wanted a setup where the person participating in the demo as a driver felt like they were playing a racing game or something. We had some concerns that the person participating as a developer would be having like more fun. I really wish I had an air quotes in Animal Crossing. That was like a perfect air quote opportunity. But we wanted to beef up the driver experience because we were concerned that the developer experience would be what people were really going for. We were super wrong. Everybody just wanted to drive it. But this meant that we would need to be able to control the steering with an actual wheel and the throttle and brake with actual pedals. So we knew we were going to have to modify the donkey library. We also didn't want to mess with manually dumping the images and steering data during a live demo. It's time consuming and you have to shut the whole thing down. So we decided we were going to automate that and move the work to GCP. I also wanted a TV screen in front of the driver's seat so that they drove using the feed from the car's camera. And since things aren't already complicated enough, let's throw in some computer vision and put a green screen around the track. So to start on updating the controls, the standard donkey car is easiest to control with a web app on your phone. That's kind of what it wants to do by default. It wasn't interactive enough for us though, and it didn't give us the driving experience we were looking for. The library calls its various moving pieces parts, and it does have experimental support for a number of different physical controllers. PS4 controllers work pretty okay. These have been fleshed out more since then, though I haven't messed with them. But the one that it came with for a race wheel didn't quite work like we wanted with the Logitech G29 we had. I think our race wheel was just a little bit too new. However, there is some documentation on adding new parts. Donkey just explicitly supports this, so we wrote our own. I know the code is hard to see in the little box, but that's okay. I will hand out the code for this. The race wheel part requires ZMQ and PyZMQ to work, and it works by requesting the current values from the racing wheel and pedals via a ZMQ proxy running on the machine that the racing wheel is plugged into. In our case, we had an Intel NUC hidden under the driver's seat and a script using evdev to watch the race wheel. Actually, a whole lot of this demo ran because of that ZMQ proxy. This is just a snippet of the wheel object on the car. It does also have a couple more methods on it for running threaded and polling for updates, but it's way too much code for a slide deck. And again, I'm totally happy to provide the complete code for this part for anybody who wants to do this themselves. Once the part's added, swapping out the standard controller is a one-liner. You just need to SSH into the Raspberry Pi on your car, open up manage.py, and add it as the controller instead of the default joystick controller object. So in our case, joystick controller was replaced with just wheel. To make the driving experience feel a little bit more like an actual car, we're doing some processing on the values from the race wheel before they get sent to the car. The standard library does not really account for things like throttle scale or steering veer. So we have two helper functions here doing that math for us before sending the values over to the car. Otherwise, the throttle feels really awkward. It's super touchy. If you just tap it, it's going full speed ahead and you're absolutely going to crash. And the steering feels I don't know, kind of jerky. It just didn't work super well. We did also allow for customization of force feedback on the steering wheel to make it feel easier or harder to turn. What we found was that typically people loved screwing with that while somebody else was driving it. They almost always wanted to push an update that makes the wheel super loose or super, super hard to turn. Usually they wanted to mess with a coworker. So that was always fun to watch. But without this math here, driving the car using the wheel and pedals is still totally doable. It's just awkward and unintuitive compared to the way you drive a real car. Let's talk about the driver's seat. The track is circular, so obviously the driver needs a way to see what the car sees to know when and how to turn the wheel. Otherwise, you're going to be blind half the time. It's also necessary if you want to drive the car to the other side of your office and bang it into a coworker's door repeatedly, which is incredibly fun, and I very much recommend it. To accommodate this, the NUC under the driver's seat is going to need to do a little bit more work. What we ended up with is a SANIC web server doing most of the heavy lifting for the back end and a Vue.js app for the front end. Instead of storing all the training data in a directory on the Pi, we reroute each frame and the associated steering data through the ZMQ proxy under another topic. An async function subscribes to that topic, as well as a few others handling things for our CI/CD pipeline, the race wheel data, and some other things required for updates. And according to whatever the current customization settings are in the config file, processes the data. At the bare minimum, our Vue.js app on the driver's screen is displaying the raw camera data from the car, the current build, and buttons to record or upload new training data. This is the overhead view for the crowd that's also showing how many artifacts, the build number, vulnerabilities, and the most recent build time, how long it took to get an update onto the car. I will not show you the code for the Vue.js app because it's possibly the single ugliest Vue.js I have ever written. It was never meant to see the light of day, and I never expected to be writing a talk about this part of the demo. So that's going to stay in the dark. It's a Vue.js app. There's nothing revolutionary about it. But it worked by using JavaScript bindings for OpenCV, which I didn't know existed before this, and an open WebSocket to just continually redraw the images from the camera topic on our ZMQ proxy to a canvas element. So at this point, the car itself functions the way we want it to. You can use it the way we want you to be able to use it, but it doesn't look as cool as we think it should. So let's make things a little bit harder and give the driver some nice scenery to look at. Otherwise, it's just going to be staring at people's feet. You know, nobody wants to see that. So let's stand a bunch of green poster board around the perimeter of the track and do a green screen. So I will admit that this was not part of the original plan for our proof of concept. It was feature creep from an executive who thought it sounded cool. I was very, very new at the time and full of imposter syndrome and very eager to impress my boss. So, of course, when he asked for it, I was like, yeah, I can totally do that. No problem. I did not actually have any idea how to do this. I had to learn as I went. It turned out okay. It worked. And here's what it looked like and how you could do something similar. It's actually it's super, super fun, whether you're building a green screen for a car or just for something else. It's computer vision was really cool to learn. So in its simplest form, a script like this works by using OpenCV to read in a frame, convert it from RGB to HSV, which is hue saturation value, and create a mask out of any parts of the image that fall within a range of HSV values that you define. You set a high and a low. You then use that mask to crop the background image you want and replace the corresponding spaces in the original image. To get the edges closer to perfect, you can erode and dilate the mask, blur and smooth it a little bit as well. You can see I did that a few times. There's a little bit of guesswork involved in finding the right high and low ends of your HSV range, and lighting does affect it. So these steps help you fudge it a bit. For instance, the lighting in our office where we tested this was way better than the lighting in the conference center where we did the actual demo. And it looks much nicer in our office than it did on the conference center floor. But we did what we could with some fudging. Then you just convert it back to RGB and return the frame. It's way less complicated than it looks, honestly. It turns out that leaving it static is actually crazy disorienting, though. We needed it to simulate scenery on a drive, and if the image didn't appear to move as if you were driving past it, it's super, super disorienting. It made it actively difficult to drive the car around the track. So to make it look like it's moving, we used the current angle of the steering wheel and starting X and Y coordinates to calculate how far we needed to move the area to crop for the background from one frame to the next. Because remember, we've got all of the steering data and everything in our ZMQ proxy. So we have all of the data we need to do this. We also used a scale variable to increase or decrease the speed of the pan, which made it feel like the driver was going faster or slower. And we did also allow for things like image filters and different backgrounds to be applied as some of the updates people could push. These also took place within the green screen strip. Things like going from the desert to the countryside to outer space, inverting the colors, flipping the image vertically, which made it nearly impossible to drive. And people loved doing it once they saw one of their coworkers was really starting to get comfortable and go really fast, because they almost always immediately crash. All of these use functions that are already built into OpenCV, so there is no magic or hard work involved there. But let's automate the process of training a model in case we want the car to drive autonomously. Because remember, it can do that. Most people wanted to drive it manually, but it can drive itself. In its current state, the process looks like this. You enable training mode to begin recording, drive some laps, then stop the car, dump the images and steering throttle info to your laptop, use the Donkey CLI to train the model, and then manually move the model back to the car. It's a pain. Automating it was actually relatively low effort once we got over some hurdles related to TensorFlow on GCP. Since we were getting our images and corresponding steering data from the car via our ZMQ proxy, we were able to just pass that data along to a TubWriter utility, also running on the NUC, to collate the data, then pass it up to GCP to train the model there. So whenever a new model was available, the driver's UI would just update to reflect that availability and allow the user to use that instead of driving the car manually. We mapped some of the 8,000 buttons that exist on a Logitech G29 to be turn on training, turn off training, self-driving mode, manual mode. So this was still actually pretty slow. It took like up to 10 minutes, but it's still faster and easier than stopping the car, manually moving the data over, waiting for the model to train on a laptop instead of on like dedicated server, and then moving the model back. So at this point, there is pretty much no reason to stop the car unless you need to swap out one of its batteries. It's got two. And now we're mostly automated at this point. It's maybe more complicated than it needed to be. We didn't really need to automate the training, but it was fun. So that's how the flashy bits work. Like I said, it's not revolutionary, but it is fun to build, and it's a great opportunity to teach yourself about hardware, machine learning, messaging queues, and computer vision all in one project. Personally, I did a lot of learning and growing as an engineer while building this, and I hope you try it and learn something too. If any of you happen to be experts in all of these different disciplines, I guess call me because I've got questions. I don't know anybody who's an expert in all of these things, so there should be something for everybody to learn when trying to do this. And I don't know about you, but I need fun, wholesome, tinkery projects to keep me busy at home right now. I can't play Animal Crossing literally all day. So I can't publish the entire code base for this demo, but I am more than happy to share the code for the components I talked about here, including the racewheel part we wrote, the ZMQ proxy, and the green screen, so you can build something similar yourself. If you do decide to take a crack at it and have questions, you can just DM me on Twitter or email me, whatever. It's not like I've got anywhere to be right now. So if you extend it even further, if you build this and like make it cooler, if you find some like horrific bug in my code, also please tell me. I would love to see what you do. And also, I wrote most of this code like 9 months ago, and I have some regrets personally about the way I did some of these things. So if you have complaints about it, also DM me your complaints. Again, my name is Kat Cosgrove, and my Twitter is Dixie3Flatline. Again, my slides will be up at that bit.ly link, as well as a raffle for a Switch Lite and a copy of Animal Crossing. So thank you for paying attention to me, and thank you to the organizers for putting this together and babysitting all of us and spending your personal time setting up something that maybe was a gamble whether or not it would take off, but it seems wildly successful and everything has gone so smoothly, and I really appreciate it. Thank you.
Thank you, Kat. That was so amazing. I'm in over my head in the best way. We have a couple questions from the Q&A. The first one, how long did this project take?
It took 4 engineers, well, 3.5 engineers. Our boss was trying to help, but he didn't actually have that much engineering time to dedicate to it. It took 3.5 engineers, about 2.5 months to build the whole demo, which included the like fixing over-the-air updates for edge devices portion. That was like the bulk of our time. Building the first time I built a donkey car, the donkey car alone took me, I don't know, like 2 hours to build and get a functioning model. Since I had to teach myself things like messaging queues and computer vision, the parts of the demo that I talk about here I think it took me about a month of spending like maybe half of my engineering time each day working on these.
And how long did it take you not to say Donkey Kong every time you said Donkey Car? That's just a personal question for me because I hear Donkey Kong even when I know you're not saying that.
Yeah, I think I got over it somewhere like halfway through the first day of the conference. So we were all saying Donkey Kong, Donkey Kong, Donkey Kong,
yes.
like during development. And it became a joke. And then we got to the actual conference and had to remind ourselves to like be adults for a minute.
Fair enough.
Yeah.
All right. So one more question. Since you mentioned it, how do you push back on feature and scope creep?
I think it depends. Now, since I'm a developer advocate, I'm fairly independent. I don't have like a team leader that I need to go to most of the time if there's a problem. On that team, we did have a team lead who is fantastic. And if he had been in the room for that meeting, he would have stopped me. Yeah, he would not have let that happen. That was entirely my fault. I should have known where the line was, but I was very new. And I didn't know where the line was or how to recognize what's an unreasonable request. But
yeah, it's a tough, that's a tough question on any project, I feel.
It is. I think step one is have a good team leader that you trust to have your back. But if you can't do that, then realize that setting boundaries is a good thing. And going above and beyond to please, just like saying yes to feature after feature after feature because you want people to like you want management to think you're capable, can actually hugely come back to bite you.
Yeah, absolutely.
You're going to take on a whole bunch of, you're going to look good for a minute when you first say yes. Sure, we'll add that.
That might be when you feel the best too.
Yeah, you're gonna say yes, and you're gonna look good to management then. But then when you ultimately can't do it, or you have to start canceling things, cutting features a few weeks later because you realize you've got more on your plate than you can handle, you're gonna look real bad. So it's step one is learning that setting boundaries is good for both you and management's perception of you.
Yeah, absolutely. Thank you so much. People had many questions in the Twitch chat, and maybe some of them will make their way into the Discord.
Okay.
Amazing job. Thank you so much.
Thank you.
Everyone, just give a very warm round of applause to Kat for that really amazing presentation.